why is this an integral at all is really the crux of the question. Why do I have to actually stop and integrate? And if you don't have a way to communicate that well, you're going to be unable to do the integration here or know when an integration is necessary. That's what we're really getting at here. And that's why I want, and trust me, Aramis, this isn't just about you. I am very confident of the 5 people in this room who, if I walked up to this problem and said, tell me the flux, that I could be very disappointed in their performance. Now, I'm not going to call them out, but none of them asked questions yesterday either. You follow me? And some of them had to get an earful yesterday because they were stuck in my research class. But some of them were able to walk away without having to pay the penalty for it. Now, making sure that everybody understands that. And so if you don't want me calling you out on it, you better understand this, because otherwise we could do things different. So I know the shape of the frickin' wire. I know everything about the wire. I know how wide it is. I know how long it is. I know how far away it is from the other wire. I know all sorts of stuff about its dimensions. You need to understand why we have to actually integrate. Go ahead. I'm willing to let you tell me.
Okay. Is it because of the magnetic field that the farther away it is, the different magnitude it has?
That's why I have to use an integral for this. I'm adding no matter how. Meaning it's a sum regardless of how I do it. If I just find the length and the width here, if the magnetic field were constant everywhere in there, then me saying B times W times L, that's a summation. I've added up all the magnetic flux. It's just everything worked out where all I had to do was multiply how big the magnetic field was because it was constant everywhere in the area. And I knew how to calculate the area of the stupid shape. In this case, though, the problem is that as I get further away from the wire, magnetic field is not constant. So the reason why I think vocabulary is important here and why it's worth me being so difficult is this strip, all of the little boxes inside here, all the little tiny squares that are inside here, every one of them sees the same magnetic field strength. And I could do that all across all of those little boxes, but every little box inside here sees a different strength than the one before. So it's important that I understand that it's about how far away I am from the wire, that's the part that's changing. That the horizontal part of the rectangle, all those are the same contributions, but the vertical part of that rectangle, that's going to be an issue. When I have to sum, and I have to find a way to add it up. That's the first part. Look, there's been other ways that they've done this. This one's pretty popular. And it's popular for, I think what I hope you guys know are obvious reasons. If you're trying to write a stupid test, then this one's a good one because I can work in lots of content. I can work in Ampere's law, which is how we got the actual value for what that magnetic field is some distance away from the wire. So, because if you didn't know that, if you didn't have that memorized, you'd have to prove it. Ampere's law is the only way to prove it. So, I don't know why they just didn't ask you to figure out an expression for the magnetic field around the wire. Make you do Ampere's law here too. If you want to do the flux, you'll need an expression for the magnetic field that is in some way related to how far away from the wire we are. Which means setting up some values here that you can use in this calculation. Like I need to know how far away from the wire I am. I could just use R if I wanted. Why? It's already there. I didn't yesterday. I purposely chose just whacked out variable names because they gave us numbers. But I couldn't use those numbers in integrating. Not if I wanted to make a point. So now this sets up things like how wide is that piece? This is establishing the integral portion. That we need to have an integral variable. I need to integrate for R. I need to add up R. But how do I work it into a value that sets up an integral? Well, I recognize that I can treat this as my dA. That's why it becomes LdR. That's the area of that entire strip. And so on and so forth, and that's how we set this up. And no, I don't want to go back through all of this, because most of you understood how to do it. But you 5 who don't, can you do it? Can you do it on your own without looking at your notes? If you can, you're golden, you're fine. You don't need my wrath. If you can't, then what are you waiting for? Sit down tonight and try it. And then if you get it wrong, look at your notes, fix it, and then sit down, close your notes up, and do it again. You should be doing that for a first order differential equation too. Go back to the RC circuit, figure it out. Find the charging equation, do it. Be perfect at it. Look at your mistakes. They're gonna ask you to do it on the exam, something like this. It is likely not going to be something that we haven't already done. It's gonna be something that's already in your notes. So there's a piece of math that we've done that's been repeated again. Do it again. That's why that one where the bar fell, that's why I was frustrated with that one. You had done that integral before. I was frustrated that for some reason it felt different this time. Now that that problem is over, what? So this is where the question actually begins. You know, I didn't expect you guys to be stumbling on that part. So let's talk about this part, because this is the part that's interesting. I do need placeholders though, and you guys already have some. What do they say this is? They give me a number. What did I say yesterday for our letter? W. Okay. And did I give this a name? X. All right, fantastic. So help me out. When we were done, there's an expression for the flux here. And I know probably mu naught I over 2 pi is out front. What's the rest? Go ahead.
Mu naught I L, so that's outside the parentheses. And in the parentheses, if you leave it in terms of x, it's ln of x plus w over x.
Is that it? Any mistakes I've made? Anything I left out? Because I'm not re-deriving it and I don't have it memorized from yesterday. Okay. Can we agree this is a single loop? Okay. So if I want the EMF, then I'm going to do ddt of the flux from there. Now here's the next thing, and this is why I think Faraday's law, bless you again, you all right over there? Okay. This is why I think we get in trouble with Faraday's law, especially a problem that requires integration first and the derivative next. And students have made this mistake and said this out loud. So if you're taking notes and you want a piece of information that may or may not be helpful, but I think is, you're integrating over location. You're deriving over time. So the integral part isn't directly related to the derivative part because we have different variables involved. We have frozen time for a moment when we are finding the flux. We are picking a specific instance in time and calculating flux. So t doesn't exist in that calculation. If there's a t in your equation, it's a constant, it passes through. For the calculation of flux, we are picking a specific moment in time, so it is a constant. When we are taking the derivative, then only things that change with respect to time become relevant. So the v wasn't relevant when we were taking the integral, because there is no velocity if you have frozen time. Velocity is a change in position with respect to time. So this didn't exist when we were doing the integral because we stopped time for that instant. Now that we're back and we're working our problem and time is relevant again, other things have suddenly become constant. You know, things that mattered a minute ago that don't matter now, like W. W is a constant now. It was an integral portion of our integral variable before. fact, everything else except for x stays the same. But x is buried inside the natural log. So if we want to do this next part of the problem, we're going to have to deal with the fact that we're going to have to take the derivative of this natural log. And you have a couple ways you can go about doing it. I'm going to choose the one that I think is easiest for you guys, not the one that maybe you would have chosen on your own. So I look here and see that all of this is just some big constant. It's going to pass through the derivative. Nothing there is time varying. So can we all be in agreement to just kind of ignore that for a minute and focus on the fact that what we're really taking the derivative of is the ln of x plus w over x. And the constant's just out here someplace. Well, this is the chain rule all day long. And I found yesterday that some students don't remember the chain rule. I don't know how the chain rule is taught in your calculus class, and I don't care. I'm going to tell you how I think of it and what I do. And if you don't like my method, fine, then use calculus. He's given you a method. But I'm going to also make this easy on me to explain. And so to make this easy on me to explain, I'm going to try and make the derivative part of this as simple as possible. I know that the derivative obeys the distributive property. And because it obeys the distributive property, I'm going to split up that integral and not have an integrand, split up that natural log and not have a particularly complicated quotient that I have to take the derivative of. Because although I know about the quotient rule, the quotient rule is a pain, and you all know it's a pain. So I never use the quotient rule. I only use the product rule. Even when I have a quotient, I just break it up into two products. So I could have done x minus w times 1 over x and just broke it up into a product, done the product rule. But I don't even have to do the product rule here. I want to make this as easy on myself as possible, and I've done it. Now, I could have probably done something different. I probably could have had 1 minus w over x and done that too. That's fine. But this is a sum, and I can distribute the sum. And I already told you, I'm doing it the way I want to do it. If you have a different way, do it your way. But better get the same answer. Yes, sir?
Isn't that x plus w?
Yes. So now I'm going to distribute the derivative, and I'm going to take the derivative of this term and then subtract the derivative of this term. So let's go with the first term. The derivative of the ln of x plus w. Well, I just do the derivative of all of this as if all of that were x. So the chain rule works. So that's just going to be 1 over x plus w. But then I have to take the derivative of what was inside there. That's how the chain rule works. Minus, well, the derivative of ln of x, just 1 over x, plus the derivative of what was inside there. Chain rule. Any problem with the chain rule there? That's how I learned to do it. Take the derivative of your thing, just wherever the x is, act like the whole thing is just x and take the derivative, and then multiply by the derivative of whatever that thing was that was in there. Are you good to keep going? All right. Because that's really it. That gives me 1 over x plus w times dx dt. The derivative of w is 0. It doesn't change with respect to time. Minus 1 over x times dx dt.
Doesn't x become 1?
Nope. Why would it become 1?
Because you take a derivative of dx.
X isn't a constant. X is changing with respect to time.
Not to be the derivative with respect to x.
Right? I have to leave it that way. Because, yeah, I would only be able to do that if, yeah, I'm sorry, thank you. You explained it better than I. Now, this is the moment where I realized that this is how V gets worked into the problem. X, which is the distance from here to here, is changing with respect to time at a rate of V. That's velocity. So these jobs are just V. More importantly, you can pull them out of the function. They're the same. Once I've taken the derivative, I'm good. So mu naught I L over 2 pi times all of that. And you have the numbers for it all, but this just becomes mu naught I L V over 2 pi. And then times 1 over x plus w minus 1 over x. This is going to be my EMF. Just a little bit of interest there. 1 over x plus w is a smaller number than 1 over x. So the inside of that's going to be positive. That's nice and convenient. I would have been a little worried if it had somehow reversed the direction of the EMF due to the shape of the rectangle. That would have been weird. Luckily, it doesn't. So be clear that whatever direction we get, it's not being reversed because it's a rectangle. If you know what I'm saying, if this had worked out to be a negative number, odd stuff would be afoot. Because it would say that Lenz's law wouldn't apply and go in the opposite direction of what Lenz's law says. You understand why that could be an issue, right? So they gave you all of those numbers. You just plug them all in, right? They tell you what the x was at that instant. They tell you what v was at that instant. You know it also. I'm kind of done working the problem out. But is that okay for the derivative part? It's a nice, solid, interesting, hard question. I liked it. Yep.
What number was negative?
This. Look, there's a negative sign inside here. And I've tried to impress upon folks in, I think, mechanics more than here, but still, it applies here. Whenever you have an answer that could potentially be negative or 0, you should pay attention. Something weird's happening. If due to the conditions of the problem, it could reverse direction. You should pay attention anytime that can happen. Or worse, get a 0. We can get a 0 here. Now, the only way we get a 0 here, of course, is if W equals 0. So I'm confident that ain't happening. But it would be weird if after we worked this out, this whole thing worked out to be negative.
It is negative. That's why I was...
I sure hope not. Because how is that going to work the direction then? How do we deal with the direction? Oh, you're right. This is a bigger number than this one.
Yeah, so it has to be... Yeah.
So how does that deal with our direction then?
Did we not have to get rid of the negative?
Because the negative would have been out front.
Yeah, so there's negative out front, it cancels out, right?
But Lenz's law, guys. Lenz's law.
Well, if it is that way, then Flux.
No.
It needs to reinforce the magnetic field. So, what direction's I in?
That's in material. Why do we get a negative? Oh.
Yeah, if you put the negative in the front and the negative in the middle, then it cancels out, so it ends up being positive, I guess.
Well, I've spent this whole unit trying to ignore the negative sign in Lenz's law purposefully, because I knew we can always figure it out with the right-hand rule. But in my head, the negative sign there should be so you can figure out direction without having to use the right-hand rule. That numerically it works out, and I can't in this moment I can't wrap my head around it. So, right-hand rule is still going to tell us if the current in this wire is this direction. I don't remember what direction it said it was. But if it's in that direction, then we can still use the right-hand rule to determine the direction of the current in this loop as we move it away. We know the magnetic field is decreasing as you move away from the wire, so it's going to create a current that's going to try and maintain a magnetic field that's in there. The only way to do that is for the current to be this way, right?
Yes.
So I'm wondering if the positive sign comes from the fact that these two currents end up being in the same direction as they are closest to the wire. but I don't really know. And I'd probably have to look more closely at the negative signs as I speak to all that. But either way. I want to talk to you about something called back EMF today. Or induction. There are so many words associated with this. Any one of these is okay. I was trained in school to call it a back EMF. All of this is induction. So using the word induction is too broad a term, but an inductor is a specific kind of device. So it's hard to impress upon you why I'm being so specific, but the law of induction and self-induction is used to create a device. Now, we've talked about, and I put the devices out there, so if you unwrap them, you've already looked at them outside the box. Those are inductors. And when I had ordered those inductors, it was meant, I ordered those last year, and clearly I was disappointed in them because we can't use them for hardly anything. They are 3 Henry inductors, and we'll talk about their size in a bit. But ultimately, an inductor is a solenoid. These are big solenoids. So they are, there's a nice solid iron core in there. They have a very small wire that's got a lot of wraps around it. They have a maximum amount of current they can support without frying the paint on the enameled wire. But ultimately, they have so much internal resistance, they ended up being useless for me as experiment devices go. So as much hope as I had on using them, they were not as good as the capacitors. We can't use them the way I thought we would to do simple inductor experiments. We'll do something with them, but I was practicing all during lunch today to kind of as a diversion, and all I did was fry 3 bulbs. So I am currently not happy with how they're working out. But I want to start with a simple circuit as a means of describing to you what self-induction is. We have been ignoring this all year. And so that whole thing about Mr. Shelton lies to you guys that Mr. Liebel brought up, it's not a lie. It's just that you weren't prepared to hear the real story. So now hopefully you're prepared to hear the real story. I left this out. And what I left out was pretty minor for a circuit like this, but not non-existent. So if I have an EMF here, which I am specifically labeling with no subscript, okay? Be aware of that. I'm specifically labeling it without a subscript. If you want, I can use a capital V because I'm going to have another EMF here in a minute. So if you need me to use a different letter here, speak now. So it's V. And I have a resistor here. You guys are well aware that if I close this switch, there will be a current developed based on Ohm's law. And that current will travel this way through the circuit. Well, if I do close that switch, and we say that that switch is being closed at time equals 0, this current that's being developed is going to generate a magnetic field this way into around my wire. Right? So that there will be a magnetic field into the page all around that wire. Everybody understand that? Now, there was no flux before, but this constitutes a closed loop with length and width. When I close the switch and generate this current, I create a change in flux. Correct? That change in flux, by definition, must create an EMF. An EMF that wants to produce a current to oppose the change in flux. I'm being very careful about my word choice here. I would consider writing some of them down. I'm going to finish. The EMF that is produced must be produced in such a way as to create a current that opposes the change in flux. That means there must be an EMF created in this direction so that the current would be cast in that direction to try and prevent the establishment of this flux. This is called an induced EMF and is referred to as self-induction. All circuits self-induce an EMF. You'll also know that this EMF opposes the establishment of a current, which means that no actual currents are instantaneous. When you close the switch, a back EMF is created immediately to try and prevent the establishment of a current and will therefore affect the rate at which your current builds up in your circuit. This is called self-induction. Yes?
What happens at the steady state? Does that induced EMF just become zero?
This EMF only exists while the current is changing, because that's causing the change in flux. So our steady state will be when this back EMF goes to zero. A while ago, we defined the quantity of capacitance a long time ago. And if you can think back to those days, the definition of capacitance was how much charge you could store for an applied voltage. This was a less dynamic idea. You apply a potential difference across the plates of a capacitor, moving charges from one of the plates to the other. Eventually, there's an electric field that develops to prevent more charges from being added from one plate to the next. It gets to a stopping point, and you have charged your capacitor. A device that was able to store more charge would allow more charges to move under the same voltage. So something with more capacitance could store more charge for the same voltage. It was static in description. That's not how to describe what we're seeing here. Inductance is different. If you were to describe inductance, and we use a capital L for inductance, you guys in mechanics are going to love that because we're using capital L for angular momentum. Yippee! Fun times, isn't it? We use a capital L for inductance. If we wanted to try and have a similar ratio, like what is inductance? Well, we know inductance is going to be related to an EMF. It's how much EMF you get. If capacitance is how much charge you get, then inductance is how much EMF you get. You understand why I'm saying it like that? So something with more inductance would give you more back EMF. Now, the other side of that, what causes the EMF is a change in current. So we relate it to current. So when you apply current to a system, that change in current causes a change in flux. The back EMF you receive is proportional to the change in current. So a larger change in current should produce a larger back EMF for the same inductance. However, there's something else I'm going to add here. The EMF is opposing the direction of the current, or the direction of the change in current. It's going to oppose the change. This didn't exist for capacitance. There is no opposition to this. For inductance, there is. Now, you'll remember from a while ago, perhaps, maybe, that we spent and split our time here. Part of our time was talking about the construction of capacitors. We used that definition to determine how to build a capacitor. Do you remember those steps that we did? Generally, we looked at an arrangement of two conducting pieces, you know, a couple of plates or a coaxial cable or two spheres. We only had a couple that we looked at. We looked at that arrangement. We used Gauss's law to figure out how much charge there would be for the electric field that was applied, and then used the definition of potential difference and the electric field to derive an expression for the voltage related to the charge that was there. And that's how we got that. We constructed them, and that's how we found out things like the capacitance of a parallel plate capacitor. We would derive these things based on the construction of a capacitor. Then we went and put it in a circuit. We solved this for V. We placed it in a circuit with other circuit elements. And we applied Kirchhoff's laws to this circuit to see how the circuit would behave. So we looked at the behavior of our capacitor. The order in which we do this doesn't really matter, but I want to remind you, those are what we did for a capacitor. An inductor is going to have some similar properties. And so as a circuit element goes, it makes perfect sense for us to consider that we will probably have to look at the construction of an inductor. How do you construct one? And of course, we're going to want to talk about circuits. You all done over there? Back to work here. So we have a choice of which thing we can take a look at. We can talk about how to construct an inductor if you want, or we can talk about their performance in the circuit. I want to kind of talk to you a little bit about what inductance actually looks like. And I want to talk a little bit about the units of inductance too. I think those are things that we probably need to spend a few minutes on so that you get a better understanding of what this whole thing inductance is and where it's going to come from. It will help us with the construction and how it's going to behave in circuits. So let's take a look at the units first, just so we have an understanding of what inductance is measured in. And I should point out there's something I've been kind of missing, and I wish I had spent more time talking about it. So first, if we're going to look at the units of inductance, let's look at the units that we have here in our equation. Top part's voltage, put volts there. The rate of change of current has to be amps per second. So work that out a little bit and you get volt seconds per amp. And that unit doesn't make a whole lot of sense anyways, but that's the Henry. And so inductors are measured in Henrys, capital H. The inductors that I had in the classroom yesterday for you guys to kind of take a look at, those were 3 Henry inductors, and you know how big those were. So, you know, physically large objects, 3 Henrys is a lot of inductance. And those objects were pretty beefy. They had a pretty strong iron core, and they had a lot of wraps on them because they have quite a bit of resistance. I had not said this to you before, and it came up on an FRQ I was looking at, and I wanted to make sure that I at least get this into your notes. The units of magnetic flux. Generally, oh my God, really should. There is a unit for magnetic flux. We don't have a unit name for electric flux, but we do have a unit name for magnetic flux. And remember, it's magnetic field times area, which is Tesla times meter squared. This showed up in one of the FRQs, and I've never talked about it. It's called a Weber, which is W lowercase b is the unit.
I remember seeing that in the
So
book.
I know it's out there, and I want to make sure that I've at least thrown it out there. It's not terrible if you put Tesla meter squared. You're not going to ever get points off for doing that, but I would hate for them to say that you have a solenoid and it has this many, or has a measurement, and they've given, at least one FRQ I've read, they've given a value in Webers, and I didn't want you to be confused. A Weber is a measure of magnetic flux. Okay, so I want to remind you that this whole thing about the back EMF is about magnetic fields. So the more you could ramp up the magnetic field, the more likely you can get a measurable back EMF. So in talking about a circuit that's just a single loop, bless you, not probably going to be the best way to have a large back EMF. So if you want to ramp up the EMF, you need to ramp up the likelihood that your circuit could create more flux. And you guys know the best way to create more flux is to have more loops. And that suggests a solenoid. So the symbol for an inductor would be a solenoid. And it's usually stand off from the main line of the circuit like so. So it doesn't always have to be that exaggerated, but that is generally what the symbol for an inductor is going to look like. So as opposed to a capacitor or a resistor, an inductor should appear to be a group of loops of wire like that. Now, one of the things to think about is why this would probably be the right shape is consider in this circuit, you've got already the possibility of lots of available flux because we have lots of places for that magnetic field to occupy. I mean, yes, I know there's a current in here, and that's clearly making a small magnetic field through the center. But in the area or the region where I have all of those loops, I have a far more concentrated magnetic field. So, in fact, if I can put a piece of iron in there, I'd have something that could really ramp up the size of that magnetic field. So, a simple inductor with current passing through it would create a magnetic field that way down the center. You should check to make sure. I'm following old notes, but I'm pretty confident in that. Now, we good? When the circuit has reached a steady state condition, there is no back EMF. An inductor is invisible under these circumstances because it's just passing current. An inductor is only at play when the current is changing. So I'll say it again. An inductor is invisible in a circuit when the current's in a steady state condition. Because when it's in a steady state condition, there's no change of the magnetic flux. So it's invisible. It's zero resistance. Now, that's not true at all. Actual inductors are spools of wire. Wire has resistance. So when we talk about inductors and say that they have zero resistance, we're saying that in the same breath that we're saying that the wires in your circuit have no resistance, and we know that's not true. So real inductors are going to have a resistance, generally stamped on them, telling you how much resistance the inductor coil of wire is going to add to your circuit. So be aware, although an inductor technically will have no effect on your circuit at the steady state condition, it's going to dissipate energy as heat just like any resistor. And there's no way around it. So it's hard to build the inductor circuits that we're supposed to test out, considering that they add resistance to the circuit in a manner that's difficult for us to manage. So although we can do the capacitor circuits no problem and see the little bulbs light up and turn off and all that kind of stuff, it's harder to do that with the inductors. So all of those circuits that we made first semester and talking about, where the capacitor would go and where the current would pass and all that, what's the steady state condition, what's the transient condition, what's the initial condition, it's going to be harder to build those with inductors because of the internal resistance of an inductor being so high. But here's the thing. In the circuit like we have right now, with the current in a steady state condition, if you attempt to shut off the current, so with what we've drawn right here, we decide to reduce the current. So we have, say, current I, but we're going to reduce current. A number of ways we could do it. We could manipulate the resistor here, right? If we start increasing the resistance, then the current's going to be changing. So perhaps rather than having a regular resistor in here, we take it out and replace it with an adjustable resistor. One that we could increase or decrease. If I increase the resistance, that would begin to reduce the current. If you attempt to reduce the current, the flux that's passing through the solenoid is going to be reduced at the same time. So there's going to have to be an EMF in place, a back EMF, to try and prevent the change. So if you reduce the current, the inductor will act as though a battery has been supplied to the circuit in this direction to try and push more current in this direction to maintain the current that was there. In this case, the back EMF isn't trying to prevent a current from being established, it's trying to maintain the current that was already there. Remember, the back EMF is trying to maintain the state of flux that exists. And that state of flux is based on the current that's passing through the wires. So if you attempt to reduce that current, the EMF will be created to help sustain that current. Yes?
I thought you said the back EMF opposes like the magnetic flux and current.
No. That might be what you wrote down, but that's not what I said. What I said is that the back EMF opposes the change in current. And this is doing just that. It is opposing the change in current. Thank you. That's for vanilla. It's got your name on it. It'll be here for 10th class. Unless it's drugs.
It is a phone.
Is it calculated? It would appear.
It feels calculator-ish, or the worst iPod ever made.
I don't have an iPod. It's probably a calculator. I gave it to a friend of mine for.
And they delivered it back by envelope.
Yeah, it's a little.
Good friends.
I told her I needed for physics, but.
So you try to reduce the current that's already there. There's going to be an EMF created to try and maintain it. It's going to oppose this change by creating an EMF. Now, so saying the word back EMF, that seems like a misnomer here, but the EMF is going to attempt to prevent this change. So this EMF will be created to prevent the change in what you just tried to do. Yes?
If the positive's on the bottom and the negative's on top, wouldn't the EMF be up? Or am I?
Conventional current is the rate of positive current flow, and it goes from negative to the positive side of the battery.
Oh.
Always.
I figured.
Okay.
Let me read that back.
Always.
Can you repeat that one more time? Just that sentence. Just that sentence.
Wait.
No weights. No weights. This is true. I've been doing this for a lot longer than you. Yes, it's always this. Every time I've drawn a circle with the battery that way, it goes small to big. The potential difference is increasing from small to big, always. I've been very consistent about this. So I want to maintain a current in those wires. It's going to act as though there's an EMF in that direction to push more charges that way, because we're trying to prevent them. We're taking them away. We're slowing them down. We're not slowing them down. We're reducing them. So this EMF is created to try and maintain the flux, to push them there, because they're not going. And it wants to make them keep going. I'm using as small a words as possible for you people, and you're supposed to be the smartest kids in the school.
What? No way.
I agree. I am just as surprised as you some days. Can I keep going? I mean, there's only two options here. I try to reduce the current, an EMF appears in this direction to try and maintain it. There's the other possible plausibility that instead of reducing the current, we try to increase the current. So increase the current. This could be done by reducing the resistance. So turning down my potentiometer. If I try to increase the current, then a back EMF will be created to oppose this increase in flux. So if you try to increase the current, there will suddenly be an EMF in this direction. This would be the direction of the back EMF to try and prevent this increase in current. So the back EMF, this self-inductance of our circuit, is attempting to maintain current in the circuit. That's what it's going to attempt to do. Now, there are lots of reasons you might want to do this. When I'm talking about, real circuits, there are a lot of reasons why you might want to maintain the current in the circuit. The most likely one, as you guys probably can imagine, is that we here in Florida get lots of power disruption. Finding a way to prevent spikes in EMF and in current is essential to ensuring we don't fry a lot of electronic equipment. We place inductors inside those power strips that say line conditioning. There's inductors inside there, purely to make sure that the current flows at a uniform rate. So any spike that comes through is met with a natural back EMF to prevent the spike from going through. And if there's a dropout or a brownout, there's a natural boost. The energy in that field is used to try and maintain the current. So if there's a loss in current, the energy from the field feeds the current. And in a similar way, once it's fully charged, once there's a high amount of magnetic field there, it's hard to change. It's almost like this acts like inertia for circuits. And I've talked about that idea before, that these devices, capacitors, serve a similar function for voltage. Inductors do this for current. But again, they're like inertia for circuits to help maintain a solid current in your circuit and to prevent dropouts of current. Now, we have a choice on what we do next. And based on the time remaining, we have even chance of both. I think the best thing to talk about today, since I think it will impact the most number of people, is to talk about the construction of inductors. Mostly because they're easy to construct and there's not a wide range of them like there is for capacitors. I mean, generating magnetic flux is usually best done in only one or two ways. And then tomorrow what we're going to do is we're going to talk about RL circuits. That's going to be the first order differential equation that we're going to have to solve to come up with the charging time and discharging time of an inductor. That's the thing where I get frustrated and we repeat the same thing over and over again. And you guys say, I've never done this before. And I say, yes, you have. Remember that? Yeah, that'll be fun tomorrow. We'll save that one for tomorrow. And we'll do this one today. And that way, all those people who are missing, when I make them have to do it, they'll be like, well, I wasn't here that day. I don't have to worry about that BS either. So let's talk about the construction of an inductor. And to deal with the construction of an inductor, I'm going to start with the definition of an inductor. And I'm going to solve this for the EMF because most of the time, this tends to be the equation we see for inductance. I wrote it the other way to kind of show the dependence relationship. And I do that a lot with stuff like current equals voltage divided by resistance. We don't usually see Ohm's law written like that. Usually we see V equals IR. But it's a dependence relationship, and I think dependencies are important. Inductors are the same way. The inductance is defined by how it performs in the circuit. So I believe this dependent relationship is better. But let's start here. First, the EMF we're talking about comes directly from Faraday's law. So the first thing I hope you realize is that this EMF is the EMF that is produced from Faraday's law. It's a rate of change of flux. So one of the first things to consider is that we can make this substitution. The back EMF can be shown to be directly related to the change in flux. So that will be the first thing I do, is write these things together as minus N d flux dt equals minus L di dt. Now, the next place to go from here is recognize we can cancel out the two negative signs. But we can also, I'm not sure if you know you can do this, but both of these have had the derivative taken with respect to t on both sides. Do you see that? It shouldn't be a huge stretch to realize that that must mean this can be written as Does that make sense? And of course I can cancel out these negative signs. Now, solving this for inductance, I now get something that has a little more capacitance comparison. Remember the other expression, this one we started with, required a kind of a dynamic situation to express. It would be hard for me to find a way to measure the rate that the EMF is produced because of the rate of change of the current. This is a little easier to show. This is just a comparison of how much flux you get for a sustained current. I mean, if you want to see a true comparison, consider that this is a static situation, right? A sustained current. That's very similar to the capacitance thing from earlier. An inductor is measured based on how much flux you get for your current. So a capacitor is measured for how much charge you get for a voltage. So although an inductor has a dynamic measurement, we can still define its structure based on static qualities. That's important because in this case, it's not too hard to figure out how much flux there is for a current. Right? If you think back, how many of the things that we've talked about for magnetic field have magnetic fields that are proportional to currents? Isn't it all of them? I mean, by definition, aren't they all proportional to current? That all the magnetic fields we've talked about come from current? So this looks like it will have the same kind of solvable properties. If I can come up with an expression for magnetic flux for some structure, and then divide by the current that creates that flux, that would give me a way of calculating its inductance. If I can come up with a way for figuring out how much charge there is on a conductor, and divide by the voltage that created that charge, that would give me the capacitance. That's how we did the capacitance equation. This seems like a great way to figure out the inductance equation. And we already know how to do this. For example, you know the expression for the magnetic field of a solenoid, don't you? Let's consider that for just a minute. What is the expression for the magnetic field of a solenoid? So I'm going to change it to N over L. And I hope you see why. Because I have, an N here that's on number of loops. I see something that also has number of loops in it. Seems like a reasonable thing to do. Now, let's say I do create a solenoid. and I want to measure how much magnetic flux there would be in my solenoid. So I have a solenoid. I already know that the magnetic field produced by the solenoid will be this. Can we also agree then that the magnetic flux is probably going to be related to how big each loop is? Pi r squared work for you guys, where r represents the radius of the loops. So if I say that this is a circular solenoid, and that's r, then pi r squared should be the area of each loop. That okay so far? Seems to me then that my magnetic flux through a solenoid will be mu naught I n over L times pi r squared. This is all for a solenoid. So if I want to calculate the inductance of a solenoid, I take the number of loops, I take my magnetic flux, and I divide by the current powering the solenoid. Just taking this equation, putting it there. So I think you guys see what's going to happen next here. I'm going to combine like terms and cancel things out that can cancel. And I get n squared mu naught pi r squared over L. Let's write it a little differently. All right, so I put all the geometric parts of it to the right and all the constants to the left. I think that's appropriate. If we consider that even a capacitor had geometric portions, right? Area of the plates, separation distance of the plates, that determined how much charge could be stored. Solenoid or inductors are going to have a similar geometric set of properties, where the size of the inductor is going to determine how much inductance it can provide. I don't think these are surprising. I think maybe where the L is a little surprising. Maybe not terribly so, but L is in the denominator. So if you make your solenoid longer, it's less effective at acting as an inductor. I find that to be a little bit weird because we tend to think of other things being more effective. A resistor, if you have more of that material, it does more to resist the flow of charged particles. But we have a similar kind of thing with a capacitor, but I think it makes more realistic sense. If I get the plates closer together, I get more capacitance. But this is saying if I make my loops all packed closer together, I get better inductance. And this is probably because it's concentrating the flux in one place. And the more the flux is concentrated, the more inductance, more back EMF you get. I don't think it's a surprise that the R squared is on top. Right? You make the area in which this magnetic field passes through bigger, you're going to get more inductance. And it should not be a surprise that the number of coils shows up very prominently. It's squared. I mean, the R squared makes sense because it's an area. N squared might be a surprise to you. But if you can double the number of loops, you get 4 times the amount of inductance. So the number of loops makes a big difference here. This is the construction of an inductor. There are no other ways to really make inductors. Inductors are all solenoids. Once you learn about one, you've really got it down. There has been, I can't tell you, how many times this equation comes up because it's so seldom. I don't even remember if it is on FRQs hardly at all. Where the construction of a capacitor shows up all the time, the construction of an inductor really doesn't. So you should understand how it's constructed, but they're just solenoids. All right, tomorrow is